Semiconductor fabrication, right?
The right place. Left it first.
3 minutes, right?
Cool. This is called common courtesy. Breaks for the next guy. It's tied up. It's permanent fixture. Just be like this.
You got a 5-person class?
Hmm?
You got a 5-person class?
Yeah, 5 is enough to make it. Or should we cancel the course?
No.
No? Okay. Well, I think this first day is always crazy. Even I didn't know till this morning if they had all this stuff. You know, some rooms need to bring your own cable.
Oh.
So at least we don't have to do that.
I have a quick question.
Yeah.
For the book, which
You haven't even started yet.
I know. Well, you know me, right? Which edition of the book do we need?
Which edition?
I mean, does it matter?
Syllabus. What's that?
I don't
Volume
think
5, second edition.
second edition.
Yeah. But you'll see.
It's from the bookstores. The
Yeah.
second.
Yeah, this is it.
Books
But
are not available in the library.
they should have it on reserve soon because I know last semester they did put this on reserve. They don't have the book at all, or they don't have it.
Right now they
It's been checked out.
checked out. Just
It's
only
been
one.
checked out.
Yeah.
Okay, yeah, that's something I'll ask them to get it back and put it on.
It's a
I
very
think I told
expensive
them-
book, and there are different editions available online. That's why I ask.
No, second edition.
Cool.
And yeah, I'll ask them to put it on reserve for us, because I think I asked them already, but I'll make sure that it is. In fact, I get both of the books on reserve as a general rule.
So it is must to have that book, or the other materials will cover it?
Your homework will be assigned from the book. So if that comes from the book, you need to know where it is coming from and what figure to refer for. Because we might not go exactly as per the book as far as the lectures are concerned, but homeworks will be, so to speak, by the book. Blink. Blink. Now what? Don't give up on me today. Blinked again. Okay. Something is okay. Right, let's just wait one more minute before we have this. No, we have 13 enrollment in the course. All right. This is EE5343, EE5343, Silicon IC Fabrication. For this course will be recorded. There's this camera here. There will be slides and the video for the course available right after the class. So whatever we do in this classroom during this time will be permanently recorded. So syllabus for the course. My name is Dr. Samir Iqbal. I'm an assistant professor in electrical engineering, and I'll tell you a little bit more about my coordinates on the slide. Behind this one. This is available online in Blackboard as well as on the course website, which is my lab website on the link page, and that you can access through EE homepage as well.
Are the videos will be available on the Blackboard or any other?
The link for the videos will be posted on Blackboard. For all course-related communication, we'll be using Blackboard. We'll have a little more of that as we go along. Okay. I've passed out the syllabus, and we'll go through major parts of syllabus today. There's the second thing I want to pass on is statement on ethics, professionalism, and conduct for engineering students. A soft copy is posted on Blackboard. This is a document that I would want you to sign and turn in to me in maybe a couple of weeks. That's fine. But this would be a required sort of statement that you have read and understood what is expected in terms of professionalism, in terms of different ethical aspects of how do we conduct ourselves in this, during this course. And I will be giving you a few examples also soon on what are the expectations and how do we. Okay, these, the things that need to be turned in, you can turn them in on your way out when we finish the lecture. So, there's another handout which I'll be passing out very soon from Bell Labs to Silicon Valley, and another one, there's plenty of room at the bottom, which is posted in Blackboard, and link will be given to you. So these are background reading materials, not necessarily something that you will be examined on, but more on historical perspective of what we are doing and why we are doing this. All right, so how many of you are not electrical engineers? Okay.
I will be.
You will be. I'm just asking because that tells me at what level should I start on. So devices generally are considered to be all the electronic gadgets that do some mathematical function for us, right? So in very fundamental terms, this is what a device does. Given an input, we expect some output from it. A very simple device is an inverter, where we give it a signal which we call a 1, and what we expect at the output is a 0, right? So at a logical level, that's what we call it. But in the actual electrical terms, we are giving it a high voltage, which may be few volts, 5 volts maybe, or 1 volt, but what we expect at the output is something which is very less, maybe half a volt or maybe 0.2 volt. So that difference is what a device is giving us as an output. How do we implement those? How do we make those devices? How do we practically make those devices in a silicon substrate? That's what we will do in this course. Lectures will focus on theory, and lab is where you'll actually do that. So why do we want to do that? Because there is a big industry that is doing that, and there is a continuous demand of technologies, of devices that are what we call next generation. And when we say next generation, basically what we are doing is we are pushing the feature sizes to be smaller, which gives us more real estate available on a substrate. When I say substrate, that can be a silicon wafer, right? Or there can be a wafer made of some other material, because there's silicon germanium is also something that is used for different parts of devices. But we'll focus on silicon in this course. That's the title of the course as well. So this is the major, what you call, push in the industry, where we are pushing many more of the function parts on a substrate, on a wafer, which is basically the number of transistors. And that's happening because we could make the device features smaller. Now, that's the product. What about the infrastructure? What about the equipment that we use to do that? That's exactly what we'll learn to operate in this course. So what are the different processes? What is the equipment used to carry out that process? And how do we control the outcome of a process? So we'll look at different parameters that define the output, and then you guys will carry out some of those processes in the lab. You can stop me anytime and ask a question. We go very flexible in this course. So, all that it takes to make an integrated circuit device. They start from crystal growth of material, which can be thin film of bulk or bulk. Bulk is the difference is where the whole substrate is made up of one material, and thin film is where the actual part of the substrate that we use for devices is grown on top of a bulk, which is thin film. What is meant by oxidation? How do we make semiconductor materials behave electrically different from non-conducting materials, which is essentially it is called doping. So there are two ways how do we dope semiconductor material, diffusion or implantation. How do we deposit materials? How do we remove materials? Called deposition or etching. Lithography is a direct, you can say, replication of how do we take images with the old-fashioned camera, where we had that film that we used. So we had an image, and we used to transfer that on a film, and we would develop a film. It would give us a negative, and we used negative to expose a sheet of paper, what we call the picture, right? So 4x6 glossy prints is what we get at the end. So but that technology is something what we use to transfer a design of a device from a concept into a computer design onto a physical transparent object, which can be simply stated as slide, transparency slide like we use with this projection, or a set of glass plates. We will look at more closely at what is called lithography, and we use that to transfer that pattern onto a wafer, which we do use for development of devices. So lithography is something we'll spend lots of time in developing basics for you guys. Hopefully we'll get to a process simulator where you can on computer define different parameters, change the properties of material, and before you do the actual processing, we can simulate what should be the output. We don't have it yet, but I'm hopeful we should be able to get it. So I'll update you as we get on. And then once we make different components of a working device, resistors, capacitors, diodes, how do we characterize them? What do we do to electrically measure their properties? Double E or non-double E, you guys know what is a resistor, right? What is the fundamental law that defines the behavior of a resistor?
V equals IR.
Okay, what do we call that law?
Ohm's law.
Ohm's law. Who has not heard of Ohm's law? It's good. So we all know how does a resistance behave. What does V equals IR tell us? R is a constant. That leaves us with V proportional to I. What does that mean? Yeah, I know it's very fundamental. Of course, it's first lecture, so I don't. What does V proportional I mean? Anybody?
If you increase the voltage, the current flowing through the circuit will increase.
Circuit, okay, I was talking about resistance.
Okay, yeah, the resistance is part of the circuit.
So No, circuit would become much more, what you call, rigorous. So just a resistance.
Yes, sir.
So current depends on the voltage that we apply across, right? So that voltage is nothing but difference of potential, right? And that potential will result into flow of charge, okay, more precisely, electrons, just electrons,
and holes.
and holes to travel in same direction, in opposite direction. So this is the kind of understanding we all have to think about devices, right? And I know we all know all these things, but it's been a while we haven't brushed that. So how do we characterize that then? So if I need to find out a component and I don't know if it's resistive or not, what do I do to test it? What should I do? Give me a game plan. How can we measure a component and figure out if it's a resistance or not?
And
Apply different voltage,
and measure the current.
measure the current, and
observe the correct behavior of the current.
plot it.
We could do it.
If it gives you a straight line, it means it's a resistance, right? So that's what we mean by characterization. So, make sense? I know we have done this. It seems so simple, but that's essentially what is called characterization, right? So, I know something is here in my device, and I have these two probes which I can control through external voltage source, right? So what I do is I apply what kind of, so where should the independent parameter go on the scale? This is y-axis, this is x-axis. Where do we place the independent parameter? X or y?
Y.
Y?
X.
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 Y?
X.
X. Okay, so I plot my voltage on this side and I say, okay, I apply 0.1 volt, I apply 0.02, 0.02, all the way to maybe whatever my machine allows, right? And I measure the current that comes with that. So it should be something like this if I get my values right? So now if I see the trend, I see, yes, indeed it's a resistance, right? So this is exactly what we'll do. So now we'll have to know at least what should a capacitor behave like, what should a diode behave like, right? So that is the knowledge which comes from device physics. But we'll have the recipes all for that. How do you characterize the devices which you will make with your hands in the clean room, right? So that will be the main, what do you call, the overall outcome of this course, right? So now we'll get into nitty-gritty details. Who did not get an email from me? Probably a bunch of emails from me last 10, 15 days. Who did not get few emails from me? So everybody got emails that I sent. I sent it directly to your email address from my email address. I sent it through NAV. What is that system called? And I send it through Blackboard as well. Are we all familiar with this requirement of the course? Have you all already been passed or signed up for the training already? Anybody who has not signed up for training yet? Get it done. Right? Did you get my email? Okay. So you guys know what to do.
I have a question.
Yes, ma'am.
Do we have to do even the HASCOM online training as
Yeah.
well? Both are required.
Yeah. Because that's something they, I think, require before the safety exam.
It's a whole process flow.
Okay. As far as I am concerned, Dr. Huzabri, who's the manager of Kano, he has to give me a go for you. Talk to them. My understanding is they definitely require the safety exam, passing of safety exam, right? So check with them. I think they require HASCOM. But those who have done it before, they should be able to comment. Because it's a two-way traffic. You have to, it's for your own safety, and it's for the safety of others who work next to you. There are many things which are considered very fundamental for somebody working in a clean room, but it is something, it's not rocket science, but it's something which we don't do in everyday life. So you have to sit through that training. Simple things like always add acid. It's a rule. We never ignore this. Always add acid. AAA. Always add acid. Never add something to acid. Always add acid to whatever you're doing. Does it make sense? So there's simple reason why we always add acid, because when you add acid, your concentration of acid starts with very small amount and then gradually increases. The reaction is more controlled. Then you have a beaker full of acid and then you add something. So now you have the whole acid to react. So it gives you a big blast, which is not good. So this is important for you, your own safety, and safety of those who work next to you. We have two chances for you guys before we'll drop those who don't qualify. And that will be administrative drop. So I know most of you are international students. I've been an international student most of my life. So we know that we have to be in status, so all that entails. So you need to get this out of the way, otherwise the department, NanoFab, will ensure that you guys are dropped from the course. I don't have any say in this because this is a university rule.
So the training and exam will be at the same day?
Yes, so right after training, it's a quiz basically. It's something which you should, they'll give you material beforehand to come prepared, but it's a quiz. These are my coordinates. I have my office in NanoFab. Some of you know it already, but some of you will find out. We have clean room on the first floor, offices on the second floor, and it's easy to find me there. I have dedicated office hours, which will be right after lecture, about 45 minutes after the lecture. By appointment, send me an email, leave me a voicemail, call me. We can set up a time apart from that time. If you see my door open, just drop in. So I don't mind seeing you anytime if my door is open, right? But many times we have deadlines and all that, so we work while our doors are closed, but I'll be happy to see you guys anytime. Course material, again, more will come on that. Mr. Ilyas will be the GTA for the course. He will be conducting the lab and some of the lectures as well. So and he'll also be helping me with the homeworks. So he'll be your first point of contact whenever there is something that needs clarification. He has done it for quite a number of semesters, so should be able to take care of your questions, issues as the first line of query. Right? He'll post his office hours soon. We'll start the labs from next month. Basically, we'll cover a few things, a little bit theory on a few things, clean room etiquettes. All of you will be done with your training. So we'll have first lab hopefully from the 1st of February. The NanoFab, and I'll cover many of those things, but etiquettes about what is clean room, what is supposed to be clean in the clean room, and what you all have to do to maintain the what we call integrity of the cleanliness of the clean room. So we'll cover that before we start the lab part of it. Question?
So we're not meeting tomorrow morning at all, right?
Labs? No. Labs will start from 1st February. Right? So we'll continue meeting for the lectures while I get you on speed on the basics of clean room, the attire, the conduct, the requirements of clean room, and you get your training taken care of by that time. So I want everybody to be certified to go into the clean room before we start it. Right? So it makes sense? So this will be after the last training, which is when?
24.
24. So it makes sense? Okay. Assignment, already an assignment. Just send me an email. That's your assignment. Send me an email. Write down this guy in the subject, your name in the body of the email, your department, your major, classification. If you are undergrad, undecided, just write it down. Major, professor, if you have one already.
Will you be posting these slides on the Blackboard?
Yeah, I try to do it right after the lecture. If I don't, by the end of the day, we had the lecture, send me an email, right? But generally, I try to do it right after the lecture. And yeah, I make high resolution PDF of these, 2 slides on a page, and post it on. Those who have taken course from me, they know the drill. But yeah, if I forget the deadlines, meetings, appointments, this and that, send me an email, I'll do it right away, right? And day of the lab, send it to me so I can make a mailing list for you guys. So. All right, so what will be the topics that we'll cover? Semiconductors, insulators, conductors, of course. We need to, all of these things go into making a device, right? Conductors are used to reach the device for their input and get their output. Insulators are used to isolate devices from each other, and especially a very important insulator is gate oxide. We'll see when we look at transistors what is gate oxide and why it is important. Defects in crystal, why crystalline structure is important. What are different grades of crystal that we have. So some are single crystalline structure, some are polycrystalline structure, some have no structure at all, but same material. Diffusion, the diffusion is a process which you use to incorporate the extrinsic. It was an interesting news a few days ago that New York Symphony Orchestra was playing and somebody's phone went off. Conductor stopped the symphony. It was, no, I'm not picking on you, but I read it and I was like, some people are really picky about that. I'm not picky, but it's a respect for your own classmates.
No, I deserve to be picked up. I always turn it off, usually.
Okay, he wants to be picked up, so deal with him afterwards. But, so, we have to incorporate extrinsic impurities into semiconductor materials to make them conductive, make them what you call N-type or P-type. So that defines what is the majority carrier type of it. So N-type means there will be more electrons available in that material. P-type means there will be more holes available in there. Right? So we dope them with different materials. So that's done with diffusion or ion implantation. Right? So we'll see what is the difference. Diffusion we know is just the movement against the gradient of concentration. Implantation is where we force something to go into a material. Oxidation. Oxidation is again a very fundamental process which we know in everyday life as rust, right? But we do oxidation deliberately to get material which have different electrical properties. So we'll look at that as well. And nitridation is making a nitride out of a material by incorporating nitrogen. Photolithography again, it would require a little more in-depth treatment to understand photolithography, but basically it's again translation of an idea from a computer design onto a physical transparent medium, which can be a glass slide or a transparency. And it has some parts which are opaque, some parts which are transparent, and we transfer that onto a onto a wafer. And we'll look at that, how it is done. It's a very fundamental process, and you guys will be doing it as part of your training, clean room training as well, I guess. Interconnects, metallic connections, how do we connect different devices with each other? Etch is removal of material. How do we remove different materials? How do we, I think before etch we should have deposition also. Okay, deposition is missing it. There should be deposition also. I don't know how to do it. So before we etch, we have to deposit material. So we'll look at that as well. There are physical deposition processes and there are chemical deposition processes. We'll look at those as well. Where do we see deposition in everyday life? Deposition of material.
Oxidation of aluminum.
Oxidation of aluminum? Okay, that's not deposition. We are basically, yeah, it's an interesting point raised earlier. So, oxidation of aluminum, okay, how do we, I just said what is oxidation, where do we see oxidation in everyday life? Oxidation.
Rust.
Rust. Insulator, so that's, but rust is a simple oxidation process. Do we deposit something during rusting or oxidation? What happens to the material during oxidation? There is a chemical reaction and we have growth of rusty material on top of the material which is already there. So for iron, for example, we have iron oxide, which do we call it is deposited or it's grown out of iron? What should we call it? It's grown. So that's a very fundamental difference. When something is not made to put from external sources, it's deposited. When something is made up from by consuming the material which is from substrate, which is like iron oxide, it's called growth of oxide, of growth of different material, right? So you'll have to be careful when, and you'll be comfortable in deciding yourself as you get along that deposition of materials and growth of a material is very evident when you look at it. So we grow oxide as well as we deposit oxide. When we grow oxide, we basically consume silicon and we provide certain process parameters where silicon gets used up, results into a silicon dioxide layer. And it's a process which eats up, so to speak, silicon. So if I have silicon, say 500 micron thick, and I grow oxide, or in other words, I oxidize this wafer, what happens is a thin layer or whatever thickness I need of silicon dioxide grows on top. I cannot call it deposition, right? So in this case, some of the silicon gets consumed. And there is a certain proportion, like if there is X thickness of silicon dioxide, how much of silicon is used up in there? How much is it? 40%? We'll look at those numbers. How much? 44%, right? So in this case now, the silicon is, of course, less than 500 now, because some of it has been consumed. But if I deposit oxide, that would be the same thickness, but I will deposit on top of that. So no silicon will get consumed during that process, right? So deposition is something when we, so again, where do we see deposition in everyday life?
Bottom of the tea kettle.
Like, say it again.
You know, when you're boiling water, the bottom of your pot will probably get some sort of calcium carbonate or something deposited on it.
Yeah, we paint stuff. We deposit material, right? We paint things every day.
To add something new.
So we paint a layer of a thin coating of chemical, what we call paint, right? It gives a different color, right? And color would result into different absorption of heat to that surface. So all sorts of things come up with that application. I am depositing this chalk on the blackboard, right? Right? In this case, we are not using it for electrical or other properties, just using for optical properties. So you can see what do I have in my mind, sort of. So we deposit material which builds up on top of the original substrate, and it gives different properties to the surface. So we do lots of deposition in devices. We do oxide deposition, we do metal deposition, of course, to make contacts. If it's too abstract, yes, this is something which we don't do in everyday life, silicon fabrication. So bear with me, in few lectures, all of these things will make sense. Especially once you start doing this should be very clear how do these things come together to make a working device. So we deposit material and we have to then etch a material. Where do we see etching in everyday life? Where do we see etching in everyday life? Have you guys, maybe it's not everyday life, but have you guys ever seen the printed circuit boards? Have you ever made a printed circuit board as a project or something?
Yeah. The acid etching of the metal.
So we make those metal lines out of that full coating of metal by etching, by removing material at certain places. Have you guys ever seen nail polish remover? What does it do? It dissolves the nail polish away, right? That chemical reaction results into removal of a material. In a crude sense, you can call it etching, but etching is much more rigorous than that. But that's a simple example. We have a material deposited, I want to remove it, right? So you do that. So etching is done many ways for many materials, done in gaseous state than in liquid state. We'll look at that. And how do we bring all those processes together? Because to make a working device, just like any other electrical or electronic device, we have to have things stacked up on top of each other. Of course, when we open some working electronic device and we close it, there are always some spare screws, right? But not in this case. We all open some devices and then once we close it down, we always find there's some spare screws there. But not in these devices. We bring them together, so we have to know exactly which process will come after which process. Clean room, of course, is something we'll do sooner. Breakdown of the grade. This should tell you that there's a lot more emphasis on the project lab, which is your lab handbook, which you have, not handbook, your lab notebook. You have to buy a lab notebook which meets certain specifications. It's a very normal lab notebook, nothing special about it. All it has is numbered pages. Very cheap. For 20 bucks you can find something which has 100 pages that will be good enough for the whole course.
Does it have to be a clean room notebook?
It has to be not clean room notebook because that book stays outside of clean room. For the clean room, you have to buy a clean room notebook which is different, which has special pages. But we will not grade the clean room notebook. That's something where you can write down whatever, take your notes, make your take your data entries or whatever, but then you have to write it down into a neat format into the lab notebook, which stays outside of clean room. We'll work out the details, but you have to get these before February. So probably GTA can help you find some websites, but it's your responsibility to get it. Many of the previous classes have come together and ordered 10 of those, which were cheaper than buying individually. So use Blackboard to communicate with each other. So you should be able to see each other and talk to each other. Right? So that's something that I have a little more on that. There'll be a term paper. I can help you get some topics, but it's something which addresses some issue of semiconductor fabrication and processing. So I'm putting the deadline to March 20th. So probably that will be 2 months from now. So we'll have covered plenty of material for you to get some basics, right? So to know some basics. So it's a simple part. Yeah.
Do we have to show you abstract?
Yeah, you give me a report. Give me a. It's a detail is given in the syllabus. So if you look at the 5th page. So, say yeah, 5. It's up to 6 pages. So it's your call. So maximum 6 pages. Use. So there are certain requirements given there. Font size 11 or larger. But 10th week. So we have 16 weeks. Right? This is 10th week when this is due. So should have plenty of time to discuss the topic with me, to get your foundations in place, and I can suggest some topics as well as we get along. Right? So this will be after the spring vacation. So you'll have some free time to think about it. Start early. Don't wait for spring vacation. So at least start rolling some ideas as you get along. Right? So 3 distinct sections: abstract, synopsis, and solution. So I'll share the first page with the rest of the class. So whatever you write, that will be circulated with everybody else. And then you can, about 10 minutes to talk about your idea. Okay, so lab notebook, this will be collected at least twice during the semester, unannounced. So the idea is that once you get done with your lab on Friday, before next Friday, you should complete it, should be up to date. So you have a week from your last lab to bring it up to date. So next Friday, it might be collected, right? So the idea is to keep you on track on your experiments. So it'll tell you, the grading tells you that I'm not too big on homeworks, right? So it's not, the course is not on your homeworks. Maybe homeworks will be 2 or 3 questions which will be straightforward from the book. The most emphasis on your skills in the lab, on your handling your way for doing your process, because that's where you learn the fabrication, right? So a lot more, it's probably a lot more intellectually challenging for you to actually think about what is there on your wafer and what next step you should be doing, right? So that's something should tell you. So all activities, experiments that you do in the lab should go in there. Some headings, suggested headings given, and the book should have printed numbered pages. And there is a reason for that. We'll see once I give you this next handout. We'll see why this is important. It's a practice that you want to do. Data, plots, analysis, of course. Characterization, once you do characterization, I need to know how does it look like, why you reach your conclusions of whatever you do, right? So maybe you are taking measurements on your oxide thickness, should be able to relate to the process, right? What are some simple examples of process and process outcomes? You guys are engineers, right? At least, if not, like you guys are all engineers. Must have done some process and set up some variables and then you got some output, and how do you do? What? Give me an example.
Yeah. Oxide growth is the process, thickness is the outcome, you characterize it,
Right? So oxide growth is a process, and the process, of course, we haven't thought about it, but generally it's a furnace. You put your wafer in, you set some temperature, you flow some oxygen through, right? So those are process parameters. You wait some time, let it grow, and then you take it out and you measure the oxide. Those are your outcomes, right? Some simple everyday life example. Give me a simple everyday example. Have you guys used GPS? You guys use GPS? Sometimes my GPS gives me a different reading than my speedometer. A lot of times. It's always 2 miles ahead, which tells me that my car is showing me 2 miles less than what it is actually doing. Right? The process is fuel consumption, and how much RPM I get is what is your output, right? Simple engine. Make sense? So these are the kind of things whatever process you do, what do you expect, what do you get? Expectation, simple formulas. These are all processes which are very well described, well understood, well modeled. See, what do you expect, what do you get? I need to see your take on why your results would be different than what you expect. Right? We'll walk you through all this. It's not something that it's me against you. We'll walk you through this. Exams, 1st of March. Final is 10th of May. I haven't decided, again, those who have done this before, to do it an in-class or a take-home. We can discuss this when we get close to middle of February. Right? I know this was interesting to see that today. Everything that we do will be posted on Blackboard. It's an interesting tool, gives you access to it whenever, wherever you are. Right? So it doesn't clog your email address or my email address. So if you have to share homework, don't email me to us. These files are big. They clog your email and my email address. So post it on Blackboard. Right? If you have an assignment, which is maybe term paper, I'll open an assignment for you. If you don't know how to use it, I'll send you a link. Talk to them. ITAP, no, not ITAP, what is OIT, or talk to me or GD, and we'll help you how to navigate through Blackboard. Right? But that's something where we'll do the whole communication. It keeps a permanent record. We don't have to haggle over deadlines or time of submission. Blackboard will be keeping track of that for us. If you are late, talk to me. If you cannot meet a deadline, talk to me. Guys, I'm not a mercenary who keeps track of deadlines and chop off heads. If you're late, cannot meet a deadline, talk to me. I'll extend the deadline. I'll do that. The goal is not to what you call play tug of war with you guys. The goal is to help you succeed, to get you to the next level of understanding. Right? So we'll use that. And it's very easy for me to change the deadline, and it's applied for everybody. Right? So this is also something I like about that. Books, of course. You'll remind me about putting them on reserve. You'll remind me about putting these on reserve?
Yeah.
Okay, let's do that. So my understanding was they're already there, but they seem to be not. Okay, now let's talk about that statement of ethics. 3 things which we know that they're not good. Sometimes we are not sure what constitutes or what is right and what is not. Right? So generally we all know that cheating is bad, plagiarism is not good, collusion is not allowed. But we are not clear. And there's nothing wrong, because we all come from different backgrounds, different undergrads, different cultures, different countries. So we have to be on the same page. That's why I want to cover this And I've given this handout for you to, the statement of ethics, so you have to understand it. And it says, I've read and I understand the above statement. In addition, I understand that in order to ensure fairness was to it, exam will be proctored and possibly videotaped. So you have to agree, if not ask. Some things which are part of the syllabus, of course, I don't have to say that I will not tolerate cheating. Plagiarism will result into 0 for first occurrence and reduction of letter grade in the final grade. Collaboration is encouraged, but you submit your own work. It might seem confusing and difficult to comprehend that I can sit with this gentleman and work out a problem, right? I can collude. But how do I submit my own work? Because once I do the final writing, I do it on my own, myself. Very, very separate. Because we understand the problem, but we don't know how to put it into exact framework. That's where your understanding comes in. That's where the challenge comes in. Many times it's easy to catch the collusion when both of the students give wrong answers, right? And wrong chain of thought. Don't want that, right? So you are responsible for your own works, and you have to turn in your own work. Okay, what are some examples of cheating? Don't worry, I've been sitting on that side 4 years ago, so I know all that. So let's again go over some things that I would consider cheating, and you also consider that cheating. Copying from somebody, either in exam or in homework, looking around, talking when you're not supposed to talk, looking at yourself. So there's a whole long list of things that are considered cheating. On assignments, we don't do that. We don't take it from somewhere and submit as your own. We don't do it for somebody else. We don't take away somebody else's assignment and turn it my own. I don't fabricate data. What is fabrication of data? I haven't taken these readings, but these readings are part of my assignment. Maybe your lab work, right? Very tempting, especially Excel makes it very easy, right? MATLAB makes it very easy if you know how to use it. If you know how to get this, to fabricate data in MATLAB, guys, you're already good enough to measure it yourself, right? So fabricating data is something which tells us. And there are simple ways how do we look for data. You go and look at your lab notebook, clean notebook, and you see did you have entry of that data on a certain date, or did it come up later on? You see what I'm saying? This handout should tell you what I'm saying. So if you look at, let me just give it. Your lab notebook is a legal record of activities. If you don't know, people have lost patent applications or have been issued with patent depending on their entries in their lab notebook. Let me say it again. People have been denied patent, and the money that came with that patent, or have been given patent, depending on they had an entry in their lab notebook. If you look at this figure 6, and once you read, you'll see these figures came from the lab notebook of Robert Noyce. So in writing, it says that these are exactly the figures that he had in his lab notebook, which were used to file patent. Patent file was filed later on, but he conceived the idea earlier, and he did that experiment. So whatever we do, we record in your lab notebook. Your pages are numbered. There is no way for you to sneak in data in previous books, in previous numbered pages, right? And you cannot tear off any page of that lab notebook because it can be used as a legal record for. So fabricating data is one of the examples. For exams, again, long list of things that you cannot do. Materials unauthorized, test from somewhere, old test from somebody, hacking into my computer, or whatever. All those things come into cheating. How do you define plagiarism? Using somebody's text verbatim and submitting it as my own. But it can be fine if I put it in double quotes and cite where I get this text from. Does it make sense? Two requirements. I put it in double quote, which tells anybody else that this is not my writing. I'm just using it, and I cite it. And I tell it where exactly I took this text from. I tell you, there was an intelligent student here in this class who once turned in a take-home exam, which was completely not his writing, but he got the full marks, right? Because he had double-quoted everything, cited every answer. So he didn't write a single word. I still have it. I can graduate it. I can share that with his permission that he didn't write a single line on his own. He double-quoted everything, took it from sources, and answered all the questions, and cited every double-quoted text he gave me. Yeah? So it can be done if it's done it properly. So we can use somebody else's work and put it in double quotes and cite it. So plagiarism would be even if I copy his text and don't cite it, or you take each other's text and turn it in as your own. Okay? Have you guys ever heard of turnitin.com? Turnitin.com.
Not yet.
Not yet? Okay, Turnitin is a website which has gazillions of documents that it compares text against. So you upload the whole document, it matches the whole text with all the text, many of the texts that have been written before. It's very effective. It gives back the matches. So please don't plagiarize. I do check for those material. Write your own. We can take, okay, there is a way around. We can take some text and rephrase it and quote it. Still use it as an argument, but cannot just use it as it is and pass it on to instructors showing that it's your own work. Okay, collaboration. It's collusion if it's not allowed. So you can discuss and clarify concepts of ideas, but you have to come up with your own solution to the individual assignment. This is an example of plagiarism. So if you see many biosensors and their associated techniques have been studied and developed, just taken there, just rephrased, and cannot do it like this unless we properly cite it and expand or write it in our own words, very distinctly different from the source, right? So you'll see the slides and you can look at how used.
If we take it directly from a paper and have it under quotes and cite it there, is that okay?
Yeah,
yeah. That's not
so if it's double quoted and cited,
exactly the same line, it's fine.
Yeah.
And the citing is right there.
Right there.
Okay.
Yeah. But that tells me that you're taking it from somewhere.
Okay.
Right? This is something which you'll see in literature also. So, yeah. Citation. So I put this document from IEEE formatting there. So whenever you cite something, use this standard format for me. Some of the journals which may not be relevant for you, what you guys going to be do, but just put it up there as a reference. So send me, if you have to send me something, send me through UTA email address. I don't generally, I put it into junk if it comes from somewhere else, because if I receive it, next thing I see is I get high-five invitations. Okay. Stuff that people want to sell me. So use your UT address. Any questions? So let's get started on some basics here. So we know a transistor. Do we? Okay, let me ask. Do we know what is a transistor? We know resistor, right? Which basically is, what does a resistor do?
Resist current.
Resist the flow of charge, right? And current is, how do we define current?
Coulombs per second. That's number of particles traveling per second from a given point.
From a given cross section, from a unit cross section, right? So that's what we call current. So flow of charge, current means essentially the same thing. What is a capacitor? What does a capacitor do? Stores charge. Okay. How does it store? It has some locker room where it gathers all the charge.
This should be electrode and dielectric.
This should be electrode and dielectric. Okay. What is a dielectric? I knew insulators, conductors, and semiconductors today, right? So what is dielectric? Where does it fall?
Insulator?
Insulator. Okay. So can any insulator be a dielectric?
Think so.
You think so? Okay.
Not necessarily a good dielectric.
What is dielectric then? Okay. Insulator, we know resistor resists the flow of charge. Insulator is insulating material which doesn't let charge flow through. What is a dielectric? What is a dielectric? What is, okay, let's break down the name dielectric. What is die? Two, right? So what is dielectric? Which can, a material that can polarize. What is polarization? What does pole mean? Pole formation mean? How many poles are there?
Two.
Which pole? What are those? North pole and
That's a south.
south pole. So there are two poles, right? So we always have two poles. So a dielectric is that can be polarized. So polarized means it can be, the charge in the material can shift, right? So positive can go one side, or what we call the dipoles. Do we know dipoles? Have you guys heard of dipoles? What is a dipole? Dipole.
Something that has two poles.
That has shifted charges and turned into having two centers of charges, two poles, right? So in a neutral material, there won't be any shifting of charge. That's why it's called neutral. Everything is cancelling out. But when you create dipoles, what happens to the material? There's a local shifting of charge, right? So what we call stored charge is nothing but rearrangement of charges, which results into positive charge on one side and negative on the other side. And what causes that shifting?
Voltage.
Voltage. What kind of voltage?
Yeah.
Is it just you and me who are in this course?
It's,
Yes, we all are in this. So what kind of voltage do we need to do that? Capacitor. Can we use a capacitor with DC? Is it open circuit or short circuit with DC?
Open circuit.
Is it?
It is open to DC.
It's open to DC?
And short
Okay.
to DC.
So can we do charging with DC?
Sure.
You can charge it by.
They say no, they say it's open circuit.
I mean, but you can charge it. I mean,
It's an insulator, so it can store charge, right? But
but it'll flow for until it's charged. It'll still flow.
so if we go to its AC, how does a capacitor look like to AC?
It looks like a bandpass filter.
Short circuit. Why short? Because now we are changing so fast on our polarity that there's no dipole effect.
I mean, it's like an if.
It's like an if. But let's not go there. Let's take to DC because that's what we'll start, and then we'll build up on RC
So-
time constant.
In that case, could you build a capacitor with vacuum and 2 plates?
Yes, you can. If you can have dipole. So what's the property of that insulator that is important for capacitance?
That you can have
Dielectric
dielectric,
constant.
but vacuum
Dielectric constant.
does vacuum have a dielectric
Of
constant?
course, everything has dielectric constant, but is it good enough? That's the question, right? Because you have to have something that results into shifting of charge into what we call dipole creation, right? So shifting of charges that result into those charges which are on different poles, and once you want to suck out this charge, their shifting results into potential creation. It results into discharge of charge.
Then if you remove the source, then it will be source.
So it should result into the reorientation and creates a potential again, right? So what's a transistor? Okay, we know resistor, capacitor. What's a transistor?
It's a resistor you can control.
Resistor we can control. Of
With
course, we
current.
want to control everything. But what is a transistor? So a resistor that we can transduce. What is transduction? Transduction. Simple terms. Guys, if you have seen that, I like to talk simple language. What is transduction? Transducer. What does a transducer do?
Conversion.
Converts.
From one.
Split into one.
Right? So I want to control the flow of charge through a resistor, right? I want to just transduce the flow of charge, right? I want to have current flowing sometimes and sometimes no current, right? So so resistor is a two-terminal device, right? So you have a potential difference and then there's a flow of charge. If I add a third terminal which causes the control of how much current, how much charge flows through, it becomes a transistor. It becomes a transistor where I can control the flow of charge. Not just based on how much voltage is applied across this, but also on how much voltage is applied here. Right? Or this can be in combination with this. So we have 3 parts in a transistor called source, drain, and gate. So gate results into gating effect. It's like a gate, open gate, closed gate. It would let the charge flow or not let the charge flow. So how do we simply, what's a simple transistor that we use? It's called a MOSFET, metal oxide semiconductor field effect transistor. And what is its shape? It has a source, a drain. So this is nothing but a pocket of maybe in P-type substrate. This is called source, which is N-type, and we have gate on top, and we have gate electrode. So this is gate insulator, right? And we apply some voltage here, which results into formation of a channel or not, right? So without applying a voltage, there's no channel, no current flows, no charge flows. But when we apply some voltage on the gate, we induce. So if this is insulator and I apply positive voltage, what's gonna? Okay, this is semiconducting material, P-type material, the whole thing. If I apply positive voltage, what's going to happen here, right below the insulator? Let me make it the whole thing. So what's going to happen on the insulator? So this is an electrode. What's going to happen on the other side of the insulator? What happens when I apply positive charge? Okay, we all have played with magnets. What if I apply positive pole? What kind of charge side of the magnet gets attracted with? Opposite. So if I apply positive voltage, what's going to happen on the other side of the insulator? Negative charges are going to come close, they're going to accumulate, right? It's called accumulation. The technical term is accumulation. So negative charges are going to accumulate, right? So they accumulate here all the way. But while they accumulate, what happens is they are basically creating a connection between source and drain, which are otherwise insulating from each other. But now they are having a connection. It's called a channel. So there is a channel that's formed between them, results into flow of charge. So there's excess of electrons here, excess of electrons here. There was no way for them to go to each other, but now we provided a channel for them to, by applying a bias on the gate, right? Some basic things. If it's P-type, channel will be N-type. Of course, it has to be opposite type. If the whole thing was N-type, they would be short all the time because this is N-type and this will be N-type and this will be N-type. There would be no control over the gate, no control over the flow of the charges. It will be always flow. Does it make sense? So some basic things which you have to know, that there are N-type pockets, the bulk has to be other type of bias, right? And then for the creation of channel or for the gating, we have to apply opposite voltage on the other side of the insulator. Now this is a transistor.
And you said in a transistor there is source, drain, and gate, right? So here the gate is P-type, right?
No.
Oh,
Gate is N-type.
oh, gate is.
What do you mean? Gate is N-type. Gate is gate.
Oh, because you
So
said
transistor is
Okay.
P-type.
Transistor is P-type. Okay.
Oh no, it's N-type transistor because electrons are what are flowing through. So it's N-type transistor.
So basically, whatever is the source and drain, that is the type of the
That is
transistor.
the type of transistor.
Source and drain will always be
Right.
the same.
Because what defines the type of transistor is what kind of carriers will be flowing. So electrons are flowing here. Right? So all the electrical properties of electrons are what are important in this transistor. Right? If it was holes that are flowing through, then electrical properties of holes were important. Mobility and all those things. Right? So that defines what type of transistor. Okay. Now this is something which I made up in silicon. Right? So bulk. But this can be easily made in discrete elements also. Right? But then that will not be called, what is the keyword for that?
Integrated circuit.
Integrated circuit. Right? What is an integrated circuit? Where everything is integrated in the bulk. Instead of discrete parts, I could have come up with a, and of course, if you see the old devices, they are not, they were, I think I have a picture of that. They were not discrete, they were elements which are brought together to do the transistor. Yeah, no, this is all integrated. So we call it integrated because it's all within the same bulk. So there will be a resistance next to it, there will be a capacitor next to it, all within the integrated circuit. But then we have something called CMOS. What is CMOS? Complementary. Complementary like it's free, like complimentary coffee.
No.
What kind of complementary is that? Complements.
It complements.
They complement. They are opposite. So there's P-type and N-type devices all in the same bulk, right? So then it is called CMOS IC. In this case, it's just P-type substrate, right? And we make source and drain out of that. But what if on the same substrate I make an island which is N-type, and then I make P-type device out of that, which is exactly what has made this technology to be what it is. The complementary MOS. Right? So, how do we do all that? We have to look at So, giving you some historical perspective, that handout and this is something which had discrete component. In 1974, they came up with this guy, which is transistor. It's not IC, but it's a transistor. Then they won Nobel Prize for this, the basic concept of transistor. But they couldn't get it to something like this until they discovered the properties of oxide, or the result of heating and providing oxygen to silicon and getting that layer which was previously thought to be dirty layer, an unwanted layer, silicon dioxide, but they figured out that this has entirely different properties than silicon. Basically, this has insulating properties. Silicon dioxide was demonstrated in 1953, and then the whole push for integrated circuit came to be what it is today. And then CMOS ICs were demonstrated. So this is a much better picture of that transistor, right? So this is something which was not integrated, but then this was it was shown that there could be oxide that could be grown. So you see, apart from a few typographical changes and improved drawings, it's completely identical to the one December 1st scriptural entry in his lab notebook. So whatever you write in your lab notebook becomes a permanent record, so to speak. For this course, maybe you don't care, but if you do end up into a research lab, this matters. This is very important, what goes in your lab notebook. So this is where you'll see, and they showed that there was oxide that could be grown, and that resulted into a planar circuit where they had everything in that bulk, 4 transistors and several resistors. So within few years, it went from this to a planar transistor. So this is just again background on the first integrated circuit. Where did they make the first integrated circuit? Guess. TI in Dallas, Texas Instruments. That's where they made the first integrated circuit. So Jack Kilby was the gentleman who came up with this, with germanium-based oscillator in '59. It was given Nobel Prize in 2000. And this is again entry in his lab notebook from '58. Took about 42 years for him to get Nobel Prize in this. Right? So, silicon oxidation. So I'll let you read this handout and we'll continue from here. So oxidation, the creation of oxide, or easy creation of oxide on silicon, is probably the only thing that has made silicon material of choice. There was no other reason why they chose silicon and not other semiconductors from group 4. They found out that the oxide grown out of silicon had very different electrical properties, very different physical properties, very different etching properties than silicon, which resulted into using of silicon to be the workhorse of silicon industry. Any question?
Actually, I have one question.
Yeah.
What are you going to be making in the lab?
We'll be making transistors. Yes. Capacitors, resistors.
We'll actually make a transistor.
Yeah.
Cool.
Yeah. That's the goal, but it depends on many times how do we go in the lab. But definitely resistors, transistors,
And
capacitors and
are we also going to embed the transistor on
You're
the
not gonna,
silicon, or
yeah, you're gonna do you don't embed anything, you just
so you deposit?
done everything in the bulk.
Well,
You won't be stacking devices, you'll be doing it on a
So once we
planar.
can make a transistor and a capacitor and resistor, we can probably make an oscillator or a flip-flop or
Yeah, there
something,
is-
right?
That's unlimited options for you guys to
Nice.
do whatever you want to do. So we'll walk you through the whole process of how do we make mask, how do we translate that mask design into a wafer, and how do you make these different parts of a transistor in a substrate. Resistance is straightforward, capacitors are straightforward. It's this guy which requires a couple of mask alignments and lithography steps. Right? So, good. Let's meet on Thursday.
Are we going to be making our own masks or?
No, we'll use the mask. But we've been showing you how it is done. That's right.
So I'm thinking if the implantable device is going to go anywhere, it needs to have some of the circuitry built into the
Yeah, of
device.
course. How do you get the message out?
Otherwise, I mean, if you have to put a chip for the preamp and chip for the other stuff inside the
Yeah,
amp,
the two-
you already lost.
Yeah. It's going to be too big.
Is that? No, bioengineering. Yes. Well, there's a device I want to build, so I figured I'd take this class.
it's a good course. Yeah.
What's your name? Sahad. Oz. Nice to meet you. Oz. Oz.
You will be going over the details of this thing, the P and the next.
Oh, a lot.
Because I feel this is basic.
No,
And
no,
the
no.
WE guys should know it, but since some other department guys are here.
Yeah, we'll go through this again of the device fabrication. What is on part?
Critical part of this.
Yeah,
I know this is very basic, but
no.
for us, for mechanical guys, maybe it's not that.